Morning, guys. Gotta admit, this one caught me by surprise. Something about these snow events happening right at the tail end of our units. Not quite sure how I feel about that. But anyway, forging on. By the way, I'm away from my computer today, so I don't have a way to generate these slides all nice and pretty with, typed up deltas and superscripts and subscripts. So I'm going to be handwriting this. Hopefully it's legible enough for you. If not, post in the comments and I'll do what I can. So reviewing, we've been talking about delta H, which, if you recall, is change in enthalpy for some time. And we've said that the change can be negative, and we call that an exothermic reaction. It releases heat, and from the reaction's point of view, that is a good thing. We talked about positive changes, called them endothermic. They absorb heat, and from the reaction's point of view, that is a bad thing. We have sketched some graphs for these. They can look like this, or they can look like this. And the delta H would be computed from these graphs by doing products minus reactants. So if we look at a graph and do small product number minus big reactant number, we'd get a negative value, know that it's exo, and vice versa here, big product value minus little reactant value, positive change, and know that this is an endo. But enthalpy is not the end-all be-all of whether a reaction happens. We need to talk about a second factor, which is entropy. If you recall, during one of the previous snow days, I gave you a short reading assignment from Chemwiki introducing you to entropy. I'll repost the link to that in the description if you need to look back over it, but I'll probably talk about everything that you need to know within the context of this podcast. So, definition of entropy. It is a measure of how energy is dispersed within a system. Some people think randomness. I'm not so comfortable with that. I'm going to stick with thinking of energy being spread out within a system or a group of molecules. Its symbol is S, and just like enthalpy, it's very difficult to measure absolute entropy. So instead, we're going to be talking mostly about changes in entropy. So I want to spend most of my time talking about delta S. We have what is known as the second law of thermodynamics, which says anytime that there is a change to a system, the total entropy of the universe increases. So this can be written like this. Change in entropy of the universe plus change in entropy of a system always greater than 0. So anytime that you make a change somewhere within the universe, the total entropy, so universe plus system, is a positive value. It's always increasing. Now, there are a lot of pop culture misunderstandings of this. I'll go on one small tangent here about that, one that just kind of particularly sticks in my science craw of a mind, and it's a really, really poor argument against the theory of evolution. Now, don't get up in arms. I'm not telling you which way to believe about the theory of evolution and intelligent designer and all of that. I'm just saying this is a really, really poor argument for the need for an intelligent designer. And it goes like this. They would charge, second law of thermodynamics says that entropy is always increasing. So evolution can't be true because we have the existence of these highly organized, of highly evolved creatures, which definitely not very entropic. So they would say, therefore, theory of evolution must not occur. If anything were to evolve, it would be to create more entropy, so apes would be turning into amoebas and such things, because that would be creating more entropy. That's a really, really poor argument and shows a lack of understanding of that, and here's why. The universe is a stinking big place. So if somewhere within that universe you have a small system, say an ape, and it's becoming more complex, so that means entropy is becoming negative, you can still obey the second law of thermodynamics, because there can be a much larger positive change somewhere else in the universe to offset this. So just a bad argument. Kind of shows a poor understanding of this. Tangent over. Let's go back to talking about now how we can disperse energy within a system. So let's say it's all about motion. And there are three kinds of motion from a molecule's perspective. So scoot this up. So three ways to disperse energy via motion. The first way, molecules can move from place to place. That is called translational motion. They go from point A to point B. Second way, molecules can rotate. They may not go anywhere, but they can spin in space. Last way, if they have bonds, those bonds can vibrate. So just kind of like if you pulled a rubber band taut and then plucked it, it can vibrate. Same thing with these bonds. So our changes in motion can create entropy. So let's talk about some ways that we can get this. So moving around from place to place and rotating, these are higher in liquids and gases than in solids. So you can create more entropy if you make more of a liquid and more of a gas. Vibrational you can get by making more complex molecules. This one is sort of behind the first two here. These are much larger amounts of energy than the vibration in a bond. So I would only think about vibration if everything else were equal. So what you want to look for entropy changes is anything that creates more liquid or more gas molecules is going to be a positive delta S. Anything that reduces the number of liquid and gas molecules is going to be a negative delta S. I have here a list of reactions, and all that you guys need to do is give me a positive delta S or a negative delta S for each of these. So I would look at this. Let me find one here to do, for example. I'll look at this guy right here. Everything is gas state, so I've not gone from liquid to gas. So now what I'm going to look at is I'm going to say, okay, on this side I have 4 moles of gas, because I have 1 carbon monoxide and 3 hydrogens. On this side, I only have 2 moles of gas, 1 methane, 1 water. That means I've lost moles of gas, and so that is a negative delta S. This is sort of what I was talking about, where the vibrational is going to get trumped by the other two motions. Methane is more complex chemically speaking than is carbon monoxide. So there is a little more entropy in methane than there is in carbon monoxide. But that's completely swamped by the fact that here we have 4 gas molecules buzzing around, causing entropy. Here we only have 2 gas molecules buzzing around, so that would be a negative delta S change. So run through this list. All you have to do is give me a positive delta S, negative delta S for this. Most of these can be decided purely on whether you go from more gas and liquid molecules to less gas and liquid molecules, or the other way around. Last topic, very briefly here. This is kind of a mathematical combination of delta H and delta S. So we've got delta H being favorable and unfavorable. We've got delta S being favorable and unfavorable. How do we see which one wins out? Will this reaction occur or not occur? And that is with an equation that we call for Gibbs free energy. By the way, on this is one of the ones where your temperature must be in Kelvin. Alright, let's look at examples for this. Basically, we've got 4 possible combinations of delta H and delta S. We have negative delta H and positive delta H. As I've written this, both of these factors are favorable. Negative delta H is favorable. Positive delta S is favorable. That means this reaction is always going to happen, and we call that spontaneous. And that's going to be true because both factors are favorable. Negative H's are favorable, positive S's are favorable. Okay. Here I have the opposite situation. Both of them would be unfavorable. So this is going to be never spontaneous because both factors are against the reaction. The interesting cases are when one factor is favorable and one factor is unfavorable. I see that I made a mistake here. This is supposed to also be positive, and here is supposed to be also negative. Alright, fix that. Here we have an unfavorable delta H and a favorable delta S. So the question is, which one's out? Is this one favorable enough to offset this one being unfavorable? And that's what this equation tells us. We would need to plug in our delta H, our delta S, and a temperature, and that's going to be the key factor deciding whether or not this one is favorable or not. So this one will be this reaction will be spontaneous at higher temperatures because we want our delta G to be negative overall, and it is going to be more negative the higher the temperature term is. So we need to get the temperature high enough so that the negative T times the positive S is negative enough to offset the positive delta H. The other way that I like to think about this is endothermic. So what kind of situations do you think are best for reactions to absorb heat? When the temperature is high, because there's a lot of heat to be absorbed. And the last situation here. Here we have a favorable endothermic reaction with an unfavorable change in entropy. So this is going to be spontaneous at low temperatures. So because the S is negative, negative times a negative, that makes this value positive. So it's only going to work when our delta H, when our T is sufficiently small that this term doesn't become so positive that it cancels this term out completely. And again, the other way to think about this kind of intuitively, this is exothermic. What kind of conditions do you think it's easier to release heat into? Low temperature. Because it's a low temperature, you can put more heat out into it. So just to wrap up here, couple practice problems, and that would be, I want to make up some values of delta H and delta S, and you tell me whether the reaction will be always spontaneous, never spontaneous, spontaneous at high values of temperature, or spontaneous at low values of temperature. And let me just make up some numbers here. Let's say I have 110, negative 110, negative 100, negative 10, 100, negative 10. There you go. Your last four things to do, just look over this list. One of these reactions will be always spontaneous, one will be never spontaneous, one will be spontaneous at high temperature, one will be spontaneous at low temperature. Again, I apologize for not having sort of nice, neat slides for this. Make any comments if there's something that you don't understand, and crossing my fingers for tomorrow so we can do our last lab. Later.